Hello and welcome everyone. My name is Lucas and I'm application scientist at Zurich Instruments. Thanks for joining our webinar, New Technologies for Scaling Superconducting Quantum Computing. And today we're very happy to host Dr. Max Werninghaus from the Walther-Meißner-Institute. Let's quickly start with the outline for today. We'll start with a brief 10-minute introduction to set the context, followed by Max's 30-minute research deep dive and finish with the 15 minutes of live Q&A. And for the topics that you will learn today, you'll hear about noise-robust qubit design, automated calibration of QPUs demonstrated on a 17-qubit chip, and optimal control to achieve high-fidelity gates on qubits, including two-qubit gates. Okay, so to start, let's look at the challenges we are facing. Scaling superconducting qubits is not just adding qubits and channels. As devices grow, the calibration load explodes. Crosstalk and drift make stability harder, and finally, protecting coherence and achieving repeatable, high-fidelity two-qubit gates becomes more and more difficult. At WMI, they are addressing these challenges in the group of Stefan Philipp already since 2020, and early on in a very close collaboration with us at Zurich Instruments. And so, while Max will tell you today how they address these challenges actually in the lab, let me first show you what our role is and how we support them from the instrumentation side. Because this is exactly our quantum mission, we at Zurich Instruments, we want to accelerate the second quantum revolution, and we want to help building quantum computers. So how do we do that? The answer lies in our fundamental philosophy. We are a company from scientists for scientists. At our core, we have over 30 dependable experts who come directly from quantum technology research. They all stood in the labs by themselves, faced the same challenges, and understand what is actually needed. We are also a truly global operation. We have offices spanning worldwide, including Switzerland, China, USA, Germany, Korea, France, and Japan, to provide local support wherever it is needed. And since 2021, we are a proud part of the Rohde & Schwarz Group. This brings us two key advantages. First, access to cutting-edge technologies and resources from one of the world's leading test and measurement companies. And second, also very important, long-term stability. As you know, quantum computing is at least a 5 to 10-year journey. Being backed by Rohde & Schwarz provides continuity and innovation even as the field evolves and faces new challenges. So this combination, scientific expertise, global presence, and a world-class backing is what enables us to deliver the right solutions. Now that you know who we are, let's talk about what's actually needed for scaling quantum computing. And that is a scalable quantum control system. And for this, we need first, of course, dependable hardware. When you're working with qubits at millikelvin temperatures, hardware reliability is absolutely crucial. You need instruments that deliver precise and stable control signals every single time, because even small errors can destroy your quantum states. Second, also, of course, a scalable software. As quantum systems grow from tens to hundreds or even thousands of qubits, your software needs to grow with them. This means intuitive programming interfaces, efficient data handling, and the ability to manage increasingly complex calibration and control sequences. And third, also very important, is the right architecture. This is where everything comes together. You need a system architecture like our star topology that is scalable, minimizes latency, and handles feedback loops efficiently. So overall, these three elements, dependable hardware, scalable software, and the right architecture, form the foundation of our quantum computing control system. And what we've realized is that software is actually the crucial enabler for scaling quantum research. Let me show you why. For scaling research, like our partners at WMI, you need access to control on multiple layers. At the pulse level, you're working with microwave pulses that manipulate your qubits. Here you can define pulse shapes sample by sample, which is essential for optimal control, for example. At the gate level, instead, you're thinking in terms of qubits and quantum operations, your X gates, C naughts, and so on. You can define simple experiments like Rabi or Ramsey, or you can also already here build complex quantum algorithms. And finally, at the workflow level, you orchestrate everything, managing, for example, tune-up sequences with built-in analysis at each step. This is where automation happens and productivity scales. And in general, our open source software Lab1Q provides all three layers in one single platform. So, of course, software performance and speed are crucial in all layers, and that is why we're currently migrating Lab1Q to Rust, which will and already does significantly improve performance across all these levels, giving you faster compilation and more efficient execution as we scale. Now, of course, all these developments and innovation didn't happen overnight. Zurich Instruments has been pioneering quantum control already since 2018, where we launched the first commercial quantum control system for superconducting qubits. Together with our partners, we also established the multiplex readout standard, enabling efficient simultaneous measurement of multiple qubits. And already in 2020, we introduced the first IQ mixer-free control electronics in our second generation, and at the same time, we released Lab1Q as open source software, giving the community full transparency and control while accelerating innovation. And right from the start in 2020, WMI was one of the first partners using Lab1Q and our second generation control system. Here, we started our successful collaboration. Together, we also partnered up in the ambitious project Munich QC SC, funded by the BMFTR in Germany, with a very clear focus on scaling superconducting qubits. So overall, this early collaboration quickly led to some very impressive results by the group at WMI. From optimal control, achieving high-fidelity gates, to exploring alternative qubit designs like fluxoniums or P-mon qubits, and demonstrating automated QPU tune-up, here in particular, which Max will talk about, demonstrated on a 17-qubit chip. But here, I leave it to Max. He will explain you in much more detail what's going on. And this is exactly the kind of partnership that drives the field forward, combining our control platform with their quantum expertise to tackle the challenges of scaling. Now, before I hand over to Max, I have one more thing to mention. You might have realized that at the lower part of this slide, it's still a bit empty, and maybe you can already guess what is missing. So the only thing I want to say is stay tuned until March next year. The time to scale has finally come. All right. Before we dive into the second part of our webinar, a quick announcement. Please post questions in the Q&A panel at any time. We'll collect them for the final 15 minutes. The session is recorded, and you also receive the link and slides afterwards, along with links to documentation and also examples. Okay, and with that, it's now my great pleasure to hand over to Dr. Max Werninghaus from the Walther-Meißner-Institute for the research deep dive. So please, Max,
Yeah.
the stage is yours.
All right. Yeah. Thanks for the nice introduction. I think we will revisit some of the things you showed now in my slides as well. Let me quickly share them. This should be correct. Looks good.
Yes.
All right. Great. Then we get the zoom out of the way. Then I will start here. So exactly, yeah. As Lucas said, we are working. So I'm Max Werninghaus. I'm working at the quantum computing group with Stefan Philipp at the WMI in Garching in Munich. And today I have put together some different technologies that we are researching here to scale superconducting quantum computing. There's roughly three parts that I'm going to go through. So first of all, I'm going to show you the superconducting quantum systems at scale that we are building, because they are somewhat the basis of what we of how we think about novel components. And then I will talk about my personal research field in my group of optimal control, where we go over calibration routines and bring up of superconducting qubits and especially two-qubit gates. And then finally, something that we also published last year is the P-mon qubit, where we are investigating novel circuits that give the qubit space some protection against Purcell decay and also photon-induced dephasing. So let's jump in. Let's go into the full setup at first. So what you see here is is a schematic of the full stack development that we are doing here at the WMI. And going through that, so the WMI focuses, of course, first of all on the development of the quantum chips, which is here labeled by the 5 indicator. But of course, within our full stack efforts, especially also with our Munich Quantum Valley efforts and the Munich QC efforts, we are focusing also on the cryogenic infrastructure, the control devices, where we partner up a lot with Zurich Instruments, and then also the larger software environment, all the way to an application layer to use these systems also reliably in the cloud. So I want to quickly go over each of these parts. So for those that are listening that are maybe not as familiar. So first of all, how we house these QPUs is in these dilution refrigerators. On the left, you can see the setup that we use for our largest qubit chips, which in this case has 17 qubits. And we will look into the architecture a bit deeper also in the remainder of this talk. And as you can see, this system is set up with actually a lot more lines than is required. So we see here a lot of high density lines because we are planning to scale this up to 100 qubits by 2027. This is how it looks like, and the rough stats about this is that we bring the system down with these dilution refrigerators to about 10 millikelvin, so minus 270 degrees Celsius. Each qubit does require one cable, so that is what we see here in this schematic. This is how we supply control signals to the qubit. Each cable, of course, takes cooling capacity, which makes then this also an engineering effort to go to many qubits. And the current limit of these cryostats is about 1,000 cables. But we are working there on our consortia to extend that. Going then further, of course, what attaches to these cables and in the end gives us control over the qubits is the microwave control stack. The microwave pulses are the programming language of quantum computing. We are very fortunate here that we are working in frequency ranges of about 5 gigahertz, where the hardware is relatively developed due to Wi-Fi and also cell phone networks. And now we have also dedicated companies like Zurich Instruments that are focusing the established hardware components, but with the twist of quantum computing. So still, each qubit requires one cable, and each cable requires then a pulse generator to control this qubit. So we are now orchestrating a lot of pulses here. Going in a bit further, what happens roughly in this control stack is that we put together a control signal to generate a microwave pulse, roughly according to this schematic right here. So a couple of years ago, this was done with analog components, but right now this is all happening digitally and synthesizing the pulses directly. So to explain a bit the different components that we have here, it's useful to look at the mathematical representation of the Bloch sphere, because this pulse will be put then to the qubit and it will enact some control components that we can understand also conceptually. So looking at the base reference frame for the qubit state, this is represented on a Bloch sphere. And importantly, the Bloch sphere of a physical qubit will be rotating about the z-axis at the resonance frequency of the qubit. So we don't have a stationary coordinate system yet, but we need to transfer into that. And this we are doing by synchronizing the pulse carrier component with the qubit frequency. And what this does mathematically is that we transfer into the reference frame of the qubit, making then this Bloch sphere actually stationary so that we can talk about the x and the y component also in a meaningful way. What this gives us immediately also is, since we typically, when we derive these control components here, we have full control over the signal. So what this gives us is a phase control of the qubit, because a instantaneous phase change of the signal will mathematically translate the qubit and rotate it about the z-axis according to the phase change that we did to the signal. So this immediately gives us an arbitrary z-gate, which is very important for the control of superconducting qubits. To get full control about the qubit state, we need also these pulse components here. And if we, for instance, apply, in this case, we are choosing a simple Gaussian pulse to the in-phase component of this mixing setup here, we will see that the qubit state on this Bloch sphere is translated on its surface, and it will perform a rotation about the x-axis. And what this gives us, if we tune the parameters of this pulse correctly, is that we will get a square root x operation, which translates then for instance, the zero state to the equator of the Bloch sphere. And if we apply the same pulse, but in the other component, so the quadrature component of the signal, we will also be able to generate an orthogonal rotation component, which we then can linearly combine to get virtually all components. So now we have an arbitrary z gate, square root x, square root y components, and these will combine then to a full operability of the qubit. So this you can also mathematically investigate, but just conceptually, it's relatively obvious to see that if you do a translation about the x-axis to the equator, and you have full control about the z rotation of the sphere due to the phase of the signal, and then you do a second x rotation about 90 degrees, you do have full control to translate any point on the Bloch sphere to any target position on the Bloch sphere by just doing these three operations. That's an important, because that means by just having this phase control and one gate tuned up that translates the qubit about a 90-degree angle, we get full operability of this qubit to translate the qubit state however we want. So that makes it relatively lean in the sense that we only have to tune up this one pulsed operation, and relevant parameters to do these operations are, for instance, the amplitude and the width of the pulse, which defines in total then the rotation angle that we can do. Of course, the resonant frequency is important so that we are able to have a synchronized reference frame with the qubit. The phase control is important to control the rotation axis, and then if we want more complex control, we also add more additional parameters. Going now how this translates and putting it all together. So now if we apply this control to all of the qubits, we get in essence full controlled single qubits, and all that's missing is now that we add the two-qubit gate component, so logical operations that we can deterministically invoke in between two qubits. And in this case, what we are doing, let's look a bit further into the architecture. So we can see here these cross-like components are, in this case, the fixed frequency transmon qubits that we are working with in this architecture. And then these are the interactions of these are mediated by these coupling structures, so these elongated components in between the qubits. And this, so a unit cell of this would look roughly like this, and also the experiment that I will be showing now will be performed only on a unit cell of this architecture. So what we're dealing here with is fixed frequency transmon qubits, and we are implementing a two-qubit C-phase gate by adiabatically controlling the flux of the tunable coupler. And you can see here already, but we will dive a lot deeper into that now, how the external flux changes in this case, the ZZ shift component of the qubits, so to the joint frequency shift of the qubits. And we can see here that by controlling the external flux, we are actually able to move that from a relatively well suppressed position all the way to where we have several hundreds of megahertz of interaction strength, which theoretically unlocks very fast gates in this architecture while having also a pretty good on-off ratio. If you are interested in the experiments we did here, which focuses more on the tune-up of this gate, I can point you this paper here, and I will also have this throughout the slides and on the last slide. So going deeper now into this architecture, what emerges if we set up these fixed frequency qubits with a coupler like this is that, first of all, of course, as a function of the external flux, we do have the two qubit frequencies, which are relatively stable for low flux settings. But as we tune the flux, the coupler here in orange will tune in and interact with the qubits in a way to also shift their frequencies. If we look also into the higher states here, we can see that, for instance, the 1 qubit state will even interact with a higher coupler state and therefore produce even a more elevated shift in comparison to the bare qubit states. And this is an important thing because it gives us an actual component in the unitary that applies only to a two qubit excited state. So all of the single excitation manifolds will, of course, experience a frequency shift if we apply a flux like that. So we pulse here into this region according to this trajectory. But we will get now a state-dependent phase shift, which is defined by just the integration of this chi shift here that we only experience in the doubly excited state. This, in the end, we can then fix with virtual Z rotations to really only experience a phase shift if both qubits are excited, which is exactly the definition that we need to implement a controlled phase grade. So this on its face seems relatively simple. We want to invoke this two-qubit phase, but now we are wondering about this pulse shape on how to actually move into this region. So to start out with, a very, very easy starting point is always a Gaussian square pulse. It's roughly defined only by an amplitude and a width. And we exploit here, what I showed before, this high ZZ shift component to invoke this controlled phase shift. If we look now at what happens to the phase shift, if we scan the amplitude A, we see that okay, we get two effects here. Scanning the amplitude will at some point give us the desired pi phase shift. Or also applying or changing the width of the pulse, so effectively the length of the pulse will linearly scale or almost linearly scale the phase shift as well. So far so good. It looks like this is a relatively nice gate scheme. With well-controllable parameters. But if we look deeper, we also notice that due to the interaction of the higher states with the coupler, we also experience some qubit leakage. And this is what we are investigating in these plots down here, which also depends heavily on the amplitude and the width. And you can see that especially the width has some oscillatory components, which so I will not go into detail about how this comes to be in this talk, but you can check our paper. It depends on how you recover the population from the coupler space. So now we want to minimize, of course, all leakage, and now we have a relatively complex problem that we can only tackle with two parameters that are in principle fully chosen to implement the correct phase, and now also a zero leakage component, which makes this calibration problem actually relatively complicated. So the conventional approach, or what the community has largely converged to, and what we are also heavily using in our lab, is to use directed acyclic dependency graphs to do a full tune-up of the qubit. So how that would roughly look like is that, okay, we have a starting point. We have two qubits in this example. First of all, we calibrate the readout, then we calibrate the single qubit amplitudes, then we calibrate the single qubit frequencies. And finally, we put that together and I collapsed here this graph into a C-phase calibration, which would then entail the measurements I showed you on the previous slide. So that means though, while the single qubit tune-up is relatively linear, in here we have a very iterative component. Of course, then this is appended with also characterization measurements of both qubits, and finally also benchmarking of all single and two qubit gates to monitor a status of the system. So how that would look like in operation is then, okay, with a relatively arbitrary graph here. So we would calibrate each experiment. We can do this nowadays also in parallel, and if everything is working, we assume we have a calibrated system. Now, what we are aiming for with this DAC framework is also that we have frequent checks if a calibration maybe very much down the line is not accurate anymore. And then we develop strategies on which preceding nodes to check to get back to a calibrated state. So we would invalidate then these two components here, go back the graph until we find the culprit. So if these also fail, we have to go deeper. If we recalibrate this one and figure out that we are able to do then a calibration of our upper level nodes again, we can do a relatively quick recovery rather than just restarting from scratch and propagating all the way through this graph. What becomes very complicated now is if we have recursive or iterative structures in this graph. And this is a problem that particularly is prominent in these structures, as I showed you before, where you have high codependency of the parameters, for instance, to minimize leakage and to get to a correct phase of the gate. Here I have an example where we use the stack framework to tune up our full 17-qubit chip. What we see here is basically 17 single-qubit tune-ups that are automatically performed on the system to bring up at least the single-qubit gates. I have here some time stats. So what we distinguish between is a one-time tune-up, which really is if you are starting with an unknown system, which we currently take 28 hours for. A daily weekly tune-up, where if you have roughly an idea where your qubit frequencies are and how the pulses should look like, it's typically much quicker to get back up to a running state. And recently we also showed or demonstrated with Lucas actually that we can use parallelization to drastically bring down this time again. And what we're also not including here is an active reset of the qubits, which should give also, okay, not a direct factor of 1/100, but at least one component of the time that we need to calibrate will go with this ratio, namely the measurement component. So getting back to this problem that we had here. So we have a relatively codependent set of parameters. We want to optimize the phase of the controlled Z gate here, which we can do with the amplitude and width. But also we want to minimize the leakage of the system. And also these are dependent on the amplitude and width. So in this highly codependent parameter space, we rather want to look into more complex pulse shapes because it turns out that having two parameters for two optimization or two target metrics is not a nice way to tune up the system. So what we investigated then is, okay, if we allow for more parameters in the pulse, so for instance, going from Gaussian square to a simple Fourier series pulse, even increasing the parameters to 5 in principle allows us to drastically get to better results because we can accommodate leakage and the phase targeting at the same time in roughly 3 to 4 times reduced pulse time. So now we can implement gates theoretically even in 15 nanoseconds. Or if we go fully into a complex regime, so do a fully complex piecewise constant representation of the pulse, then ramping the parameters for the pulse definition up to 22, we get even down to 9 nanoseconds theoretically. This is all in simulation, but it motivates us then to look into more complex solutions to this control problem. In experiment, of course, we don't have we have the problem that now the tune-up will become much more complex. The parameters are largely also still codependent, and we need to now have a multi-dimensional optimization. What we use here is a CMA-ES algorithm, which works in an evolutionary fashion. It is well suited for hardware constraints, and mainly because it gathers a lot of information and minimizes the communication steps in between. It is very sensitive to correlations between parameters and can compensating very well. And it is in principle noise resilient because every iteration does a contained check. So it's not a global optimization, but every iteration of the optimizer is a comparison in itself only. So how that then looks like and what we supply as a cost function is a randomized benchmarking based, so an orbit protocol where we generate n random pseudo-identity Clifford sequences with a fixed length m instead of rendering out the entire randomized benchmarking. And what this gives us is a relatively nice and monotonous cost function where here you see what we simulated for 3 different gate fidelities. This measure and the cost function would monotonously rise with the fidelity of the gate and therefore give us a direct sensor into the performance of the gate. What we also did in this experiment is that we gradually increase the number of Cliffords we include in the sequence, so thereby moving then this line here to the right, so optimizing the sensitivity as our gate improves in quality. And you can see this here, the optimization routine and the sequence fidelity over time converges then to a given threshold and then gets reset and rescaled and can converge again. While then in here we saw if we normalize this again to the sequence infidelity that we expect, you can see that this progressively improves over several orders of magnitude. What we then can investigate is, so first of all, we started optimizing a simple Gaussian square pulse. So we talked about this before. And we get here to a relatively limited gate error, which is exactly caused by this relatively harsh optimization problem, tackling it with limited parameters. So here we get only to a gate error of about 5%. It's barely an operation at all. But of course, it shows that the effect is happening that we want, just not to a very high fidelity. If we increase the parameter set already to a Fourier series, so now including some Fourier components and some additional parameters, we converge only in twice the amount of time. So before we took 40 minutes, now we take 80. But we can see that we increase the gate fidelity by an order of magnitude now to already 99.4. And if we go to a much more complex pulse with a linear interpolation model of basically arbitrary pulse amplitudes, we take a lot more time to converge to a solution, but we can see that we can bring the gate error almost up to 3/9 in fidelity. What we can also observe here, and that's a really relatively interesting application of this optimal control approach, is that we have quite the asymmetry in the pulse, and that hinted us towards that this pulse is trying to compensate for some distortions that are present in the lines. And then we investigated this further. And what we found is that we do have long-term flux distortions, largely caused by skin effects of the cables going into the fridge. And here on the right, you can see that when playing just a square pulse, the original response has actually a response time of several microseconds, which is, of course, affecting your gate fidelity by a lot because our gates are only tens of nanoseconds long. And that means that a gate would have effects much longer than its actual duration, meaning then that gates influence each other and limit the fidelity really drastically. With then also the Zurich Instruments real-time exponential filters and the finite response filters, we are able to tune up a precompensation that we can correct the response, first of all, by using the infinite response filters to get to this orange curve, but also then going to this final green result where we really have a almost perfect step response. And the gray area that is indicated here is actually the length of the pulse. And you can see that there's quite the difference if we apply these distortions or not. And what it means now is that we now actually gain the ability to treat the pulses as a contained unit, whereas before they would influence each other and sequence makeup would very much define how your pulses would behave. So what we do then, if we apply the Fourier series pulse again, now with this distortion applied, we get actually down to a gate error of below 0.1%, those 3/9 in gate fidelity. And also if we go again with this linear interpolation, having a pixelized pulse, we can even go down to a pulse length of now 20 nanoseconds with a slightly elevated gate error, but actually comparatively increasing the gate speed by a relatively drastic amount. So both of these approaches have some merit, where, of course, the Fourier component with a very high fidelity, very workable gate time, and the only parameter count of only 7, I believe, is, of course, a very attractive choice to then work with that in our architecture. So coming now actually back to our architecture, for the last part of my talk, I want to talk still about the qubits that we are investigating here. And so largely our architecture that we talked about before, as I said, mediated by couplers and having a control line for each qubit. The qubit is actually set up to by this Josephson junction, and we create a simple, relatively simple circuit by just having this Transmon circuit, which gives us relatively good components. We have pushed our fabrication to give us about values of 200, actually now even higher values, but also 300 or up to 500 microseconds in coherence times. Another very good candidate that we are investigating in our labs and currently performs almost equally as well is the fluxonium qubits, where you gain the added benefit that your main qubit space is significantly detuned from any other transition of the system, giving you a very high anomalisity and therefore very good controllability of the system. Today, instead, I want to pose a different problem, and this is a controllability trade-off, where we want to build a qubit that is somewhat protected from the noise influences of the effects that are happening around it. So this requires a decoupling from the environment, and it requires somewhat an advanced fabrication and design. So the problem statement is also we want to still, of course, do control and readout, but that means that we have to actively couple noisy environments to the system where we supply it with the control signals and the readout signal. What we now came up with is that we have the qubit be shielded from the environment by a mediator mode. So that we can exert control on the qubit via this mediator, but can also decouple it if we want to have it in an idle state. And how this then looks like, typically what we do is we have a typical qubit coupled via some coupling strength to a readout resonator, for instance. And via the interaction Hamiltonian, you can then get a photon exchange rate that you can use to generate the dispersive shift that we use for the readout regime. So this in a detuned manner, so if we put the qubit frequency in a somewhat detuned from the resonator, we can collapse this interaction Hamiltonian to be effectively just a frequency shift, and we get this dispersive shift that lets us distinguish the 0 and the 1 state. And this is a necessary operation that the qubit needs to do in the end to function and to give us the information back that we process in it. There's of course challenges with that, because now we are coupling through the linear coupling leads to spontaneous emission via the Purcell effect. That's a relatively well-known effect, where just the T1 is limited by some properties of your readout resonator. What is also an effect is that, of course, now if the resonator is populated, this part of the Hamiltonian will also have a frequency shifting effect on your qubit, and it will, if this is not controlled, will result in fluctuations degrading the T2 time of the qubit, so the coherence time of the quantum state. What we can choose as solutions here is to either engineer the couplings or to avoid linear couplings altogether. So this is not something we can naturally achieve, though, with capacitive couplings, with typically dip couplings of choice for these structures. So what we now do with this mediator mode is that we want to engineer an interaction Hamiltonian that has a purely frequency shifting interaction as a whole. So we call it a non-direct or non-linear interaction, where now, of course, in the dispersive regime, it looks roughly the same. So we still have effectively this Hamiltonian here, even though we have now a much more complicated mediation structure with the interaction Hamiltonian looking more like this. We still get a similar dispersive shift, which now, of course, also depends on the detuning of the mediator mode. And so we can engineer then this term here with the mediator mode. This is the target of this engineering effort. The advantage here is that we get a full protection from a Purcell decay. So since we have a non-linear interaction here that does not allow for photon exchange, we are not dealing with decay of the qubit into this mediator. And we do have a controllable dispersive coupling also via controlling the tuning of the mediator mode M. The remaining challenge is then still to fix the tunability of the mediator mode and to investigate the footprint, because now, of course, the circuit gets more involved. If we actually look into the circuit, so then this is what we came up with, and this structure here encodes actually the qubit and the mediator mode, and we call this structure the P-mon qubit. So how we can interpret this is that in this circuit, the qubit mode and the mediator mode actually live on different nodes of the circuit. So you can see here, the qubit mode is fully contained in the section of the circuit that is actually not interacting with the squid loop, so thereby being fixed frequency and flux noise independent. And we have a mediator mode that is actually living in the flux loop as well, and thereby being tunable by external flux, which overlaps actually with the qubit mode and thereby gives rise to this interaction Hamiltonian and applying the conditional frequency shift that we wanted out of the system. In addition, we also get a third mode, but we can shift this by design to very high frequencies, so it does not play a role in the operation of the system. So if we look at this device, if we fabricate it, here is the actual lumped element circuit of the system that we first came up with, where then this node 0 here is the small island, and all of the Josephson junctions are oriented around it. And what emerges then is this interesting energy spectrum, where we have in red here the non-flux tunable qubit mode, and in blue we have the mediator mode that we can use then to couple to other systems. On the top here we have then also the resonator frequency, which we need to enact the readout operation. So how we can use this now is that we can define a readout point where we put the mediator mode relatively close to the readout resonator, and thereby enabling a very strong interaction of the two, and also with the qubit mode, and also an operation mode or a control point of the tunability range here, where the qubit is again largely detuned from both the mediator, and the mediator is also has a large detuning with the resonator mode. What we get here then, we can immediately see that the T2 time and the coherence of the qubit doubles immediately at the control point. And we can look actually a bit deeper into this and explain this also via the dispersive interaction that we can also measure. So what we see here is the same tunability range, and we see the dispersive interaction of the qubit mode and the resonator. And we see at the control point, we have a very suppressed dispersive interaction, whereas at the readout point, we have a very strong interaction, enabling fast readout, but also virtually a decoupling at the control point of the qubit. This we can also then verify by dedicatedly populating our readout resonator with noise photons. And the noise photon number on average is plotted here on the x-axis. And you can see that in green here at the readout point, immediately the performance of the qubit starts to drop as we have more noise photons interacting with the resonator. But if we put it to the protected position here, we can see that even though there's a noisy environment, we can keep a very high performance of this qubit, or going all the way where at the readout point or with strong interaction of the qubit, we would hardly have any qubit at all anymore. So there's a few more details to this, and what we can learn also about this is actually looking at the effects of both the T2 Ramsey and also the T2 echo time, which is here the circle measurements or the square measurements. And you can see actually some interesting effects if we look in the near regions around the control and the readout point. So first of all, the flux sweet spot are still flux sweet spots. So we get best performance if we have a flat region of the tunable range versus the flux. But the T2 star of mode A, so the qubit mode, improves as the mediator is actually tuned away, which is actually an effect that so this is this effect right here, that it improves as we go away from the sweet spot. And this is actually that the photon in these induced dephasing starts to take over here, and gives us actually a benefit for the T2 star time of the qubit. We see also that the T2 time at the control point is relatively limited, and this is something we fixed now in later designs, where we have simply moved mode B deeper into the transmon regime, and thereby are much more decoupled from the charge noise that a transmon typically has to deal with. So in current designs, also the T2 time at this control point is much better than in this design. The remaining challenge is still to fix the tunability range, and we need to somehow deal with the somewhat more complex circuit. But we are also investigating now how to translate this architecture into doing a fully scaled architecture. So we are investigating currently how the mediator mode can invoke also two-qubit interactions, and we have some preliminary results here. First of all, what we investigated is again the ZZ shift of the qubits depending on the tuning range of the qubit or of one single qubit here, and we can very highly suppress a ZZ interaction of the two qubits. So we have a elevated on-off ratio of this interaction point. What we use instead to invoke the interaction is that the qubit state actually now defines the spectrum of the mediator modes. So depending on the internal state of both qubits, we will have a shift of the transition frequencies of the joint coupling mode here. And we can now pick any of these transitions to do a state-dependent geometric phase. The geometric phase is roughly just a rotation at the Bloch sphere that encompasses a given area, which then will invoke a phase on the target state of the transition. And we can tune this to exactly also again employ a controlled pi shift of the qubit. And in preliminary results, now we already get down to a gate error of about 1%. So this makes us very hopeful that this architecture can also go to a great two-qubit gate implementation, which then would make it a good candidate for also a scalable architecture. So with that, I'm already at the end of my talk. The two papers that I mainly talked about, you can see right here. This is the people in our group, and with that, I'm open for any follow-up questions from the chat. Thank you very much.
Great. Thanks a lot, Max. Very nice presentation. We already have quite a few questions, and I'm not sure if we can make all of them in time, but we just start. And before that, just because the question was raised, yes, slides will be shared to all of you, also the recording, likely during next week. Okay, so let's start with the first question. The question is the calibration of the 17 qubits automatic, or do you do it manually? How often do you need to calibrate? And I guess this also includes, can you trigger it automatically?
Yes. Yeah, so it is growing to be more automatic. So we have this framework that I mentioned, and it can run automatically and it rarely fails, at least for single qubit calibration. Two qubit gates are a bit more involved, and there we are working on now a robust implementation of an automatic calibration as well. Typically, you want to, if you do experiments or like an application on the quantum computer, you would want to calibrate before that in any case. So we are trying to get it as fast as possible. But also to work with it, the calibration holds for about, let's say, a couple of days. We will be fine without recalibrating. But if you want best performance, you should calibrate right before starting.
Okay. Then maybe an easy question. Do you believe the money that went into and is going into the quantum computing field will ever be recoupled? For example, a 1 billion quantum computer is very unlikely to be worth its cost. If so, what do you think is the timeline of that?
Yeah. Okay. 1 billion is still quite a bit more expensive than what we're doing here. But I think yes. So okay. For instance, I mean, we do know that application-oriented people are checking the. So for instance, McKinsey did a report on the potential in quantum computing, and there's quite a bit of problems to solve. So there's really maybe I didn't touch on that in this talk, but there's really the exponential scaling that is promised by quantum computers will grow insanely quick. So once we beat the threshold, this really will solve some problems. And then there's also a lot of money to be made. And I think like equally expensive systems already exist in like high performance compute centers. This is not a novel thing that we use expensive computers for expensive problems. Probably you will not have one at home though. That's okay, I think.
Yeah, yeah. Makes sense. I fully agree. Okay. Next question, one for the optimal control.
Mhm.
How robust is the linear interpolation method to drifts in the noise?
Yeah, so that's a good question. But so the nice thing is during the tune-up, since it takes quite a bit of time, it experiences so a very good sample of the noise that you will experience in a real world situation. That's also why we believe that this in situ tune-up, so basically using the system feedback to get the best result, is very powerful because it will adapt the pulse shape to be maximally robust to the noise that it experiences. And of course, then there will be some variation to the noise that you will experience during an application. But if you encountered most of the noise, like frequency components, then the pulse will account for it as good as it can and will adapt to even like temporary spikes in noise or something that happen during the calibration. So in principle, it should be relatively favorable to use this.
Mhm. Okay. There was a short question about Lab1Q actually. Will Lab1Q be Rust on backend and still Python interface? And the simple answer is yes, exactly. The interface will stay in Python and only, so to say, the backend is replaced. For example, we replaced now the code generator to be in Rust, but of course the interface is still in Python. Okay, then a question to the P-mon. Is the
Mhm.
T1 and T2 of the mediator measured? What's the difference between it and the coupler?
So yes, we measure the T1 and T22 of the mediator. It's of course worse than the qubit. I think I don't have the numbers right here. It's not vanishing, so it is above 10 microseconds, I think, at almost all times. But it's of course worse. And we need to decouple it quite a bit from the qubit. We designed the qubit that it does not suffer from that. Um, and in this case, the mediator mode actually behaves as the coupler. So there's only one coupling structure, which is the mediator. I'm not sure if I got that part of the question right, but I think so. Yeah.
Okay, yeah. Um, yeah, a more general question from your point of view. Which qubit topology seems most likely to allow scaling to useful QPUs at the moment?
The topology. So, okay, what we are working with here is a 2D grid, which is well, as good as we can do right now, since we are still fabricating in a 2D architecture. So we are working on also having 3D integration of qubit chips. And so especially if we talk about logical qubit encoding via quantum error correction, it seems to be quite favorable to have a third dimension that you can couple qubits in. So meaning that the basically four connections that you can have per qubit in a grid is not the ideal configuration, and it seems like that it's better to put a 3D, basically a cube. It's of course also an engineering effort, and so the result of Google shows that also the 2D implementation in principle can brute force scale. So if it turns out to be easier to make 1 million qubits in 2D than 10,000 in 3D, then I think that will still win. But yeah, so that I hope I understand the topology question correctly. So that is very much still out, and it's still a question of how far we or what's easier to integrate in the end.
Mhm. Are you then already looking into 3D integration?
Yes, although then to make these 3D long-range interactions is still very complex and yeah, is
Yeah,
definitely in a research stage.
thanks. Okay, another question on the 17 qubit processor. What are the
Mhm.
average two-qubit gate fidelities on the processor, and how do you calibrate the phase angle to achieve desired 180-degree rotation?
Yes. So the 17 qubit is a prototype, and so it has not the two qubit fidelities that we showed in this unit cell example. That's because it's mainly still in development, and we use it kind of as a test bed to fix technologies and to test that we can scale everything sufficiently. So the fidelities, I believe, are below 99% currently, and they are still subject to optimization. Um, Sorry, the second part of the question, can you repeat that?
How you calibrate the phase angle to achieve
Ah,
180-degree rotation?
in case of the two-qubit gate, basically, so a very simple explanation is, so you move into the region of high interaction, and then as you are there, the phase evolves naturally and linearly. So the duration that you stay in this region will give you a given phase, and then you just calibrate the duration that you have to stay there to do an exact 180-degree rotation.
Okay. Um, Another quick question on Lab1Q here. Does Lab1Q support external devices like IBM IonQ or only the ones from ZI? And here, Lab1Q is in principle open and it also supports 3D, third-party instruments. For example, with slow control, that is, for example, signal generators or DC bias. On the higher level, it's also compatible with OpenQuasm. And that means also on the gate level, it's compatible to other quantum computer implementations and also other control system or other technologies, even for example, ions. However, integrating control electronics that are fast, that means on a nanosecond time scale is quite limited. You can use markers and triggers, but of course, Labo&Q is optimized to our own hardware. Good. A- Another question for the P-mon two-qubit gate. Which kind of pulse shape are you using for the P-mon two-qubit gate? And do you also optimize it, or how do you
Mhm.
optimize it?
Yeah, so yes, so we of course we start always with a relatively simple pulse. So we start here also with a Gaussian, and I believe also the fidelity I showed was achieved with the Gaussian, which gives us, of course, high hopes that with more complex pulses we can also have an impact here. The problem of the gate is a bit different than in the one that I explained in more detail. So what? Okay, I can share quickly what the setting looks like. Um, what we have to navigate when doing this gate is that we have a relatively crowded frequency environment. That means that we basically employ drag-like corrections. So drag is a pulse that is designed to isolate the driving frequency that you are targeting and really not influence adjacent frequencies that you are defining. So for instance, if we choose these blue transitions here, we really want to target the one of them and we really don't want to affect the other. So that imposes in principle then speed limits and spectral limits on the pulse, which is rather hard to overcome. But yes, we are working that optimal control also here. So we're using the same algorithm again to test different pulse shapes, but the limit here is somewhat more fundamental than and it's it basically limits the speed at which you can execute the gate, which is then of course at odds with the coherence time of the qubit. So we have here a bit more of a difficult problem, but we're also looking into optimal control solutions to that.
Mhm. Just looking at the time. Um, okay, then first start with another question. Very nice talk. I fully agree. Non-Clifford gate operations are essential for quantum computing. Do you have a timeline when you expect to be able to do this?
Um, Yes, you're right. I mean, in principle, we gain non-Clifford operations by just having virtual phase gates. So I showed, I believe that we have universal single qubit control. And this fully expands to universal two-qubit control. So by having just these virtual Z rotations that I showed, I can quickly bring up the slide again to uh, oh, wait 1 second. So yeah, anyway, by doing or by having the ability to do arbitrary phase rotations on your single qubits, so this part here where I showed that by changing the phase of the carrier signal of the single qubit gates, we actually gain this full control. This is also, of course, outside, so encompassing, but also going way beyond of the Clifford group because we have really universal single qubit control. All we need then is to add a entangling two-qubit Clifford gate, and we gain universal two-qubit control. So that it should be okay. So in that sense, we have surpassed the Clifford group very easily by this feature.
Mm-hmm. All right. Um, okay, so now we are at the end of our webinar. We have a few more questions, and we can take them also offline and provide answers when we also send the slides and the recording. So thanks again to Max for joining today and presenting the nice results. Thanks a lot. Thanks to everyone for joining. I hope you liked it. And then have a nice evening and goodbye. Ciao.
Yeah, thanks for having me. Bye.